Welcome to section 3.1. Oh, section 3.4. The derivative as a rate of change. Okay, this is actually a very familiar section because we've looked at this in section 3.1 and 2.1, but this time we'll just introduce different terminologies, right? Okay, average and instantaneous rate of change. Do you remember that we looked at this example where a rock breaks loose from a tall cliff, and then we talked about the average rate of change for the first 2 seconds, and then from the interval from 1 to 2, and these were the answers, which just really it's just delta y over delta t over that interval 0 to 2, and for letter B, it's delta y delta t over the interval from 1 to 2, and we looked at this. So remember that the equation we used was the free fall equation, which is really y equal to 1/2 gt squared, where g is 32 feet per second square, and then that's if it's in the English unit, and it's 9.8 meters per second square, and so that's why when you multiply a half of 32, that's why you get 16t squared, because this is in terms of feet. All right, so let's carry on. Some more terminologies. That's just the free fall showing it. Okay, now let's go ahead and look at motion along a line. So more terminologies: displacement, velocity, speed, which is really we kind of talked about it in part of it in section 3.1 and 2.1, acceleration and jerk. Okay, jerk, this is a different meaning. It's more of talking about, has to do with speed, velocity, etc. Okay, suppose an object is moving along a coordinate s-axis right here. So just imagine this is your object moving along that way. This is the starting position, and an elapsed time of delta t has passed, so from here to here. So when we say the displacement of an object over the time from t up to t plus delta t, so if you think about it, okay, delta s is really just delta y. So it's f of t plus delta t minus f of t. So it's the displacement from this point to this point, okay? So it's like the amount traveled from time t up to time t plus f of t plus delta t. So that's your delta s, right? So suppose we want to graph the position as t changes, okay? Remember, this does not portray the path of a motion of the object. This is graphing the position over time. So if you have a starting position from here at time t, and it moves on up to that s of t, or the distance traveled over this time period, and if it's increasing, that means the derivative, of course, of the lines tangent to the curve would be positive. And if you're going in the opposite direction, that means the derivative of s with respect to t would be negative. Okay, so when s is increasing, and the slope, of course, of the line's tangent would be positive. If s is decreasing, then the slopes of the line tangent to the curve would be negative, which brings us to the term velocity, or instantaneous velocity. So when we have the average velocity of an object over a time interval, when we take the average, that's just like your delta y over delta x. In this case, it's delta s over delta t, because our delta x is really now with respect to time. So the average velocity would just be delta s over delta t. Now, if we take the limit as delta t approaches 0, then we get this. So really, when you have a velocity or instantaneous velocity of a position function, then it's just the derivative of s with respect to time. So the speed is just the absolute value of the velocity. So if you think about it, your ds by dt sometimes could be negative, or it could be positive depending on whether s is increasing or decreasing. So if you just take the absolute value of the velocity, then you just get the speed. Like here, your s is increasing, so it's got the derivative is positive, because remember the derivative is just the slopes of the lines tangent to this curve. And if it's decreasing, then the slopes are negative. Okay, so a rock breaks loose from a tall cliff, and we already discussed this. I'm just looking at this example, okay, recalling it from 3.1 and 2.1. Now, suppose we find the velocity and speed of the falling rock in this same example at t equal to 1 and at t equal to 2. So now, because we already know the differentiation rules, instead of taking the limit, so now instead of, so it's going to be s prime of t would be the limit of s of t plus delta t minus s of t. Well, here it's y, so I guess we'll have to put y there. Right? Over delta t as delta t, so instead of h, it's just delta t approaching 0. So instead of all that, what we're going to do is just use the differentiation rules. Okay? So we'll use the equation function. All right, so the free fall function would be y equal to 16t squared. Right, so A, we've covered that. B, we've covered that. So we're just gonna look at this time. Okay, so your y equal to 16t squared. So y prime of t would just be 32t because of the power rule, and then multiplied by the constant rule. So this is just a derivative. Okay, so and then to answer the velocity and speed of the falling rock at t equal to 1, so that's your velocity, which is y prime of t. Okay, and then at t equal to 1, we just substitute v of 1. That's going to be 32 times 1, right? Feet per second. So that's going to be 32 feet per second. Now, what about at t equal to 2? So your v of 2, which is really your y prime of 2, is just 32 times 2, which is equal to 64 feet per second. Okay, so that answers the instantaneous rate of speed. Instantaneous rate of change is the same as your velocity. Now, what about the speed? Well, the speed is just the absolute value. So, absolute value of v of 1 is the same. Absolute value of v of 2, which is just the absolute value of y prime of 1. Absolute value of y prime of 2 will be equal to, this is 32, this is 64 feet per second, okay? Now this is just the velocity graph moving along a horizontal line. So the one we talked about is that, okay, we looked at this graph shows the velocity of the position function. Okay, so the velocity is the derivative, so v of t is just s of t taking its derivative. So this is really a slope function. Now what does this mean? From 0 to 1, we see that v is increasing from 0 to 1, so that means it's just speeding up. Okay, and then from 1 to 2, it's constant. So you have a constant speed if you think about it. And then from 2 to 3, it slows down. Now what happens from here on down? When you have a negative velocity, it's just changing its position, its direction. So you're changing your direction, so you're moving backwards. because the derivative s prime, which is the velocity, is negative, then it reaches its maximum speed right here, right? Or maximum velocity if you think about it in the opposite direction. And then it slows down again, stops right at this moment because now the velocity is zero. So if the velocity is zero, you're at a stopping point from from time 5 to 6 seconds. And then it speeds up from 6 to 7. The position of that object in motion is now increasing, so the velocity is also increasing. Okay? Acceleration. Now here is another term that we need to remember or to learn. Acceleration is just the derivative of the velocity with respect to time. So it's defined as a of t. So take the derivative of v with respect to time, which means you're just taking the derivative of the position function twice. So this is the notation for second derivative. Okay, the jerk is the derivative of the acceleration. So it's the sudden change in acceleration, basically, is what the jerk is. So it's the derivative of the acceleration with respect to time. So if you differentiate this once more, you're taking the higher order derivatives, the third derivative of the position function with respect to time. Okay? So near the surface of the Earth, all bodies fall with the same constant acceleration, and we talked about this, which leads to the free fall equation. And that changes when it's with respect to time t seconds or with respect to meters instead of seconds. So that g just changes to 32 feet per second square, or it becomes 9.8 meters per second square in the metric unit.